Hello students, now we'll see about the Maxwell's equation in its final form. So this table represents the Maxwell's equation in the differential form, the integral form, and from which law it has been derived. So the Maxwell's first equation has been derived from the Gauss law. The Maxwell's second equation is because of the non-existence of the isolated magnetic charge, and the Maxwell's third equation is derived from the Faraday's law, and the Maxwell's fourth equation is derived from the Ampere's law. So in the differential form, the Maxwell's equations are represented over here. And in the integral form, the Maxwell's equations are represented over here. Okay, now we'll go to the Maxwell's equation 3. So Maxwell's equation 3 was derived from the Faraday's laws. We know that Faraday's laws is nothing but the induced EMF is equal to minus of d lambda divided by dt. We also know lambda is equal to n into psi. So we can write that is nothing but the Lenz's law also. So Lenz's law can be written as induced EMF will be equal to, instead of lambda, I have replaced with n into psi. So that is nothing but the Lenz's law I said you. So just replacing, I'll get minus n into d psi by dt. Therefore, the induced EMF can also be equated to the electrical field intensity. So that is integral E dot dl. Therefore, we also know that psi is equal to surface integral B dot ds. So far in the previous sessions, we have seen all these equations. Now substituting the psi value in the induced EMF, we get, that is substituting this psi value in this induced EMF, we get induced EMF is equal to minus of surface integral S dou B by dou T into ds, considering the number of turns of wire, n is equal to 1. Okay, now this is also induced EMF, this equation, first equation, and the second equation is also the induced EMF. So since both are the induced EMF, we can just expressing the induced EMF in terms of electric field intensity and in terms of dou B by dou T, I mean magnetic field intensity, we can equate both the things. So this will be line integral of E dot dl, which will be equal to minus of surface integral of dou B by dou T into ds. Now this is of line integral, this is of surface integral. So now try to convert using the Stokes theorem, the line integral to surface integral. So we need to convert this left hand side, which is in the line integral, to surface integral using Stokes theorem. So E dot dl line integral can be converted to surface integral of del cross E into ds. Therefore, we'll just substitute this equation 4 to equation 3. Therefore, what we'll get in the left hand side, we'll get surface integral of del cross E into ds, which will be equal to minus dou B by dou T into dt. So in both the sides, surface integral is there. Therefore, both the sides ds is also there, so that we can cancel all those terms, and the remaining term will be del cross E is equal to minus dou B by dou T. So this is how we have derived the Maxwell's third equation. Now, Maxwell's fourth equation is, we got it from the Ampere circuit law. So what is Ampere circuit law? H dot dl, that is in a closed loop, closed path, H dot dl will be equal to the enclosed current. This enclosed current can also be written in terms of the surface integral using J dot ds. So therefore, the total current involves both the conduction current as well as the displacement current. First, we have to know the meaning. What does you mean by the conduction current and the displacement current? So conduction current is nothing but the current through a resistive element is called as a conduction current, and the displacement current is the current through a capacitive element. You call it as a displacement current. So according to the Ohm's law, a current through a conductor of resistance R is given by the basic formula, Ohm's law formula, I is equal to V by R. The same way, the current through a conductor can be written as I suffix C, which is equal to V by R. I is equal to V by R formula. Here R is nothing but rho L by A, where rho is the resistivity and A will be your area of the conductor and sigma will be the conductivity and L will be the length of the conductor. So sigma can be represented in terms of rho. So sigma is equal to 1 by rho. So substituting these things in R, we get, I'm trying to write the R equation in terms of sigma, we get R is equal to L divided by sigma A. Therefore, substituting this R value in this IC equation, we get IC is equal to V divided by this R value. So we can get V divided by L divided by sigma A. So just rearranging this, we get the conduction current will be equal to V sigma A divided by L. So this V is nothing but again your electric field intensity into the length L, length of the conductor. Therefore, your IC can be written as in the place of V, I can replace with EL. So EL sigma A divided by L. So this L and this L will get cancelled. Therefore, the conduction current will be equal to E sigma A. So conduction current density can be represented as IC is equal to IC by A, where IC by A is nothing but your E sigma. Therefore, we can write your current conduction JC will be equal to sigma E. So this is how we derive the conduction current. Now we'll see what is the displacement current density. So that is the current through the capacitor, that you call it as the displacement current density. So the current notation is high. Since it is displacement current, I'll put a suffix D. Similar way, the previous case, I put I suffix C. Suffix C represents the conduction current. Here D represents the displacement current. So ID is equal to dQ by dt. So now what is Q? Q is nothing but the charge. Q is equal to B into C. So I is equal to C, substituting in the place of Q, B into C, I'll get C dV by dt. Now what is my C? C represents the capacitance effect. So it's nothing but epsilon A by T, where epsilon is the permittivity of one medium, A is the area of the parallel plates of the capacitor, and D is the distance between the two plates. Therefore, I can write I is equal to, already I have I is equal to C dV by dt. In the place of C, I'm going to replace this. Therefore, I is equal to displacement current. I is equal to epsilon A divided by D into dV by dt. We know that again V is equal to E into D. Therefore, I'll just replace this V in the place of V, E into D. Therefore, I'll get ID is equal to epsilon A by D d epsilon d divided by dt. So this differentiation with respect to this E. Okay, so this d can be cancelled. Therefore, the displacement current will be equal to epsilon A dE by dt. This is epsilon, this is E. So dE by dt. Therefore, I can write, bringing this A to this left hand side, I can write displacement current is equal to divided by A area, which is equal to epsilon into dE by dt. We know that the electric flux density D is equal to epsilon into E. So I is nothing but the displacement current density. We also know the displacement current density J is equal to sigma E. Therefore, I can write J, that is the displacement current density, which will be equal to dou D by dou T. Now, we'll write, it is in the beginning itself, we said it is the sum of the conduction current and the displacement current. So here JD represents ID by A, that I represented as JD, and this epsilon and E are represented as D. That's why JD is equal to dou D by dou T as I write. Now we know that the H dot dl, nothing but the closed loop, in a closed loop, the magnetic flux density will be equal to conduction current plus the displacement current. So conduction current, we have found the value as sigma E, and the displacement current right now we have found the value as dou D by dou T, and the integration with respect to S. Therefore, H dot dl is equal to surface integral of J plus dou D by dou T into ds. So this is in the left hand side is in the line integral form, and the right hand side is in the surface integral form. So we need to have both the sides, left hand side and the right hand side, as surface integral or either line integral. So by using the Stokes theorem, we'll just try to convert the left hand side line integral to surface integral. So this H dot dl will be converted to surface integral of del cross H into ds. Now replace this term over here. So therefore, we'll get surface integral of del cross H ds is equal to surface integral of J plus dou D by dou T into ds. Now both the sides we have the surface integral, both the sides we have the ds, so that we can eliminate those things. And the remaining terms will be del cross H is equal to J plus dou D by dou T. Either you can have it in terms of J, or that is the conduction current, or else you can replace the J value by sigma E. Now from the Maxwell's first equation, which is derived from the Gauss law, we know that surface integral of d dot ds is equal to the charge q. So this can be converted. This charge q can also be written in terms of volume integral. That is volume integral of rho v by rho v dv is equal to q. Now both the terms are representing the charge q. So we can equate both these values. So surface integral of d dot ds is equal to volume integral of rho v into dv. Now we'll try to apply the divergence theorem. Divergence theorem is used to convert the surface integral to volume integral. So the left hand side we'll try to convert this surface integral to volume integral. So surface integral of d dot ds will be equal to volume integral of del dot d into dv. Now replace this second equation over in the first equation. Therefore we'll get volume integral of rho v dv is equal to volume integral of del dot d dv. So both the sides, volume integral is there, both the sides dv is there. So just cancel out those terms. The remaining will be del dot d is equal to rho v. So this is your Maxwell's first equation in the differential form. Now we'll go for the Maxwell's second equation. Maxwell's second equation is surface integral of B dot ds is equal to 0. So this was arrived from the magnetic laws. The total flux in any closed surface is equal to 0. That way we have arrived B dot ds is equal to 0. Now apply the divergence theorem for this. Divergence theorem is nothing but converting your surface integral to volume integral. So if you convert B dot ds into volume integral, you will get volume integral del dot b dv is equal to 0. Therefore, we can conclude, since both the sides have a volume integral, this thing we can conclude as del dot b is equal to 0. Now we can write the Maxwell's equation in the phasor form. So in the phasor form is nothing but you're going to replace your epsilon with j omega epsilon. So in the differential form, we can write it as del cross H is equal to sigma plus j omega epsilon into E, and del cross E is equal to minus j omega mu into H. And similarly, del dot D is equal to rho V and del dot B is equal to 0. Under the integral form, the Maxwell's four equation can be represented in the following way. Thank you.